Okay, very quickly, this is the way the dispersed to nanocatalyst progression has been occurring in the oil industry since about 2 or 3 decades. Conventional hydroprocessing, the lifespan of those catalysts is, let me change this for good, 4 hours.
Thank you.
And that's it. Yeah. Conventional hydroprocessing catalysts usually decay in stability very quickly and in relatively few months or years. And then the oil industry have been trying to develop technologies for dispersed catalysts that could be smaller, so the mass transfer problems can be superated, and that is the history that shows that Viva Oil came with with a process for using small iron-based particles for conversion of heavy oils. ACAMP MNT produced also a while ago a technology based on iron sulfates. Petróleos de Venezuela produced a technology called HTH, then converted in HTH plus, and they started working with them on that regard. MCO was developed by ExxonMobil like 30 years ago, and it's usually nanoparticles of molybdenum deposited on carbon black. The particle in total was in the micron range, but the active molybdenum particle was in the range of nano. So the nano thing in the industry and in catalyst preparation in general is not a new idea. It's about that every day in the catalyst manufacturing. You try to disperse the best you can the metal particles that will be deposited in the support. The support gives high surface area, then you extend the activity of the catalyst by nano-dispersing particles, microcrystals on top of that support. The thing is that those ceramic materials, those supports are porous, and then the molecules have very high limitations to penetrate in that porous network, and they will deactivate relatively fast by coke and metals deposition in the mouth of those pores. Then the progression toward a nano dispersion or ultra dispersion of the active phases became more and more an idea in the last decade. We developed HTH plus, which is a single molybdenum nickel particle dispersed in a residue, and that showed much higher activity and reduced considerably the mass transfer control of the process. Eni came also with a technology that they are currently developing for processing heavy vacuum residues. And I also participated in the development of aqua processing, which is replacing hydrogen using steam and using nanocatalysts. This was the first nanocatalyst application in industry. We developed the setup for that. So it's nothing really very new in terms of bringing to the process itself the production of nanocatalysts, dispersing that in the reaction media, and even recovering them after the process. Then when I decided to come to Alberta, I just came with the idea of producing in situ processing. Now that in Alberta in particular, I don't think anywhere else, in Alberta we have confined reservoirs, the zone where the oil is being produced, we have already created injectivity, because SACD does that. SACD does just creation of injectivity between a producer and an injector. Then catalysts can penetrate that porous network because they may be in the range of an agglomerate of asphaltenes. Then they can flow as long as they are dispersed in a fluid media. That fluid media may be the oil itself, and that is the idea we are handling with this. But don't make yourself false ideas also. We have to control very well the agglomeration processes. Nanoparticles that are produced at 30 nanometers, if they agglomerate in a cluster of 6 particles, they will become in an average particle diameter of about 85, 90 nanometers already. If you produce 2 nanometers particle, because anybody, I have to say, anybody can produce very small nanoparticles. It's an art, it's very well controlled, it's a science, I would say. can produce very tiny particles. The problem is that they will tend to agglomerate as soon as they get together in a reaction media at 300, 250, 400 degrees C. So what you can produce in the laboratory and probably manipulate very well at very low temperature will not stay as a nanoparticle at the higher severity conditions, such as the ones required to convert heavy crude oil. So I'm going to skip this, but there is a very good field that opens the use of nanoparticles. As I mentioned, preparation of nanoparticles can be made by many different ways. We are using emulsions, and more than emulsions or microemulsions, we are using transient emulsions. We are using emulsions that exist only in few seconds or minutes at most, and we decompose them very quickly. And by controlling that decomposition media, we can produce a large variety of chemical active species that may control several different kind of processing, such as activating hydrogen, hydrocarbons, and steam as well. So I'm going to pass very quickly. We have developed nickel tungsten series, cobalt molybdenum series, molybdenum tungsten series, and many other materials. We also have developed nanocrystals of iron silicates, zeolites, etc., that can be used for applications of this kind. So that art, well, I think we managed that very well. Another thing I wanted to tell you is that we don't pretend to install a refinery down there. In a metaphoric way, some journalists use that metaphor. I am allergic to it because I know that creates a false impression. What we want to do is to reach the upgrading level that would produce a transportable oil. This is the process I contribute to develop by changing the NanoCatalyst to a NanoCatalyst formulation. This is HTH process. And this is high severity obtained with those nanoparticles with a bitumen from Venezuela. We can see that the hydrogen consumption here is very high. But we don't need to produce this. This is a 32 API gravity oil. What we need to produce is about 18, 19 API with a viscosity such as you can transport and pipeline everywhere, no problem. Then when we reduce our expectations to that, then we reduce an order of magnitude the consumption of hydrogen. And we only need about 50% conversion of that bottom of the barrel to be able to get that transportation level. That is in the range of 16, 17 API and about 250 centipoise.